Until now we have come a long way, but in molecular orbital theory we have learned how to handle only homonuclear diatomics, H2 plus, H2, F2, so on and so forth. But we do not want to stop there, right. We do not want to talk only about homonuclear diatomic molecules. We want to talk about molecules like these which are neither homonuclear nor diatomic. This, by the way, is chalphosphine C, and what you see here is the output of an energy minimized structure calculated using the quantum chemistry calculation software, computation software GAMIS. It is pretty old now. This is from our paper that was published I think in 2000. The work was done in 1999. The calculation was done to rationalize an experiment that I had performed. The experiment took a day. The calculation took a year using state of the art supercomputer of that time, and that is because the molecule is so large. But you can do quantum chemical calculations of molecules that are this large, molecules that are neither homonuclear nor diatomic, and you can get useful results. Like in this one you can see this red one as usual is oxygen, the small white ball is hydrogen. So, we see that this OH hydrogen comes perilously close to another oxygen. There is a hydrogen bond, and then that affects this property of this huge molecule in a very significant manner. So, of course, we will not be able to go all the way where we will know how to calculate how to do quantum chemical calculations for a molecule like this, but let us see first how do we handle diatomic molecules that are not homonuclear, heteronuclear diatomic molecules, and then let us see how do we handle molecules that are not diatomic, how do we handle polyatomic molecules using molecular orbital theory. So, the first heteronuclear diatomic molecule we want to talk about is hydrogen fluoride, and here I will take help of some experimental result. The experimental result that I am showing you here is from photoionization spectroscopy, and we will have reason to refer to photoionization spectroscopy later on in this discussion. What it does essentially is that it measures ionization energy. Okay. So, what photoionization spectroscopy tells us is that ionization potential, ionization energy of hydrogen is 13.6 electron volt, we already know this number. For fluorine, the smallest ionization energy we get is 18.6 electron volt. So, that would be from the 2p orbital. For HF we get an ionization energy of 13.4 electron volt, which is very close to the value of 13.6 electron volt for hydrogen, and we get another one for 18.8 electron volt, which is very close to the ionization energy of fluorine 2p. So, what we understand from this experimental result is that there is one molecular orbital in HF whose energy is very close to that of 1s orbital of hydrogen, and we have another orbital whose energy is very close to that of 2p orbital of fluorine. So, when we go ahead and when we do the quantum chemical treatment, we get this expression. The higher energy orbital expression is 0.98 into wave function of 1s orbital of hydrogen atom plus minus 0.19 psi f, and for the lower energy one it is 0.19 psi h plus 0.98 psi f. These are not normalized, so that the sum of coefficients will be 1. So, we have an orbital lower energy that is close to that, which is very close in energy and in nature to an orbital of fluorine. There is another one that is very close in behavior with an orbital of hydrogen. So, what we see is that unlike homonuclear diatomics, we can have molecular orbitals which have greater contribution from one atom or lesser contribution from one atom. So, we can have unequal contribution from the two atoms, which leads to, as we are going to discuss, polar covalent bonds. Again, from your high school you would have studied about polar covalent bonds, and we know many examples. HF, OH in water, all these are polar covalent bonds. This is how polar covalent bonds show up in an MOT treatment. And now let me show you the full energy diagram as constructed from molecular orbital theory. these energies, relative energies are more or less okay, they are more or less drawn to scale. So, this is the orbital which has energy close to that of hydrogen atom. So, this is mainly like hydrogen 1s orbital. Point to note here is that energy of fluorine is much lesser than energy of hydrogen. Fluorine orbitals is much lesser than the 1s orbital of hydrogen, as we had discussed when we talked about homonuclear diatomic molecules of second row. Okay. So, the lowest energy one is mainly fluorine. Okay. Let me go a little further. See, what we see here is that we have sigma orbitals that are made up of a linear combination of hydrogen 1s orbital, fluorine 2pz orbital, fluorine 2s orbital, right. 2pz has the right symmetry in which it can show overlap as we had discussed earlier. So, all these three should contribute to the linear combination, but what happens is that the contribution comes from square of coefficients. Contribution of the fluorine 2s and 2p orbital for these two sigma orbitals, bonding sigma orbitals, is much more than the contribution of the hydrogen atom 1s orbital. And similarly, for this 3 sigma orbital, it is still a linear combination of H1s, F2p, F2s, but contribution of F2p and F2s is really small compared to that of H1s. So, it is a mainly hydrogen atom orbital. Okay. Then you have this 2px and 2py orbitals of F2p, which do not have the right symmetry for sigma bonding. So, they are non-bonding orbitals on fluorine. So, we call them exclusively fluorine orbitals. Okay. And then how many electrons are there? We have 4 pairs, we fill them in. So, we see that the 2 sigma electrons are mainly on fluorine, they are on hydrogen also, okay, but mainly they behave like their property of fluorine atom. They are distributed in 2s and 2p orbital of fluorine atom, to a small extent in the 1s orbital of hydrogen atom. And what about these 2 pairs? These are the lone pairs on fluorine atom. Remember lone pairs, if you just draw Lewis dot structure, you will see that you get 2 lone pairs on fluorine 2p. That is what we get in molecular orbital theory as well. The only additional information is that we get to learn that in case of HF, these lone pair electrons on fluorine reside in pi orbitals. Okay. So, this is a picture that we get since the electron, since there is a more contribution of fluorine orbitals, if you draw the electron distribution or constant probability surface, you are going to get something like that, lopsided distribution. In fact, it is more lopsided than what it appears to be in this cartoon, right. So, unequal contribution from the 2 atoms is nicely accounted for in heteronuclear diatomic molecules by molecular orbital theory. And what you need to remember is that orbitals must have comparable energy and compatible symmetry, so that they can participate in linear combination to form the molecular orbitals. I will say that again, atomic orbitals must have energies that are close by to each other and compatible symmetries, so that they can participate in the linear combination for constructing the molecular orbital. So, for HF, the linear combination involves H1s, F2p and F2s. If you go higher up in the periodic table, for HCl, well, H we have no option, it is 1s. But for chlorine, now the 3p and 3s orbitals have energy that is close to H1s, and that is, those are the valence orbitals anyway. So, good thing is you can form this linear combination and you can get energy diagram like this. For bromine, now it has become predictable. We have 4p orbitals that have energy that is close to that of H1s. All these are drawn roughly to scale, and we have shown different things. In this diagram, for example, unfortunately I should have cited the source, but I have forgotten where we got it from. But what we see is that we also get to draw the MOs. This is how the MOs will look. You see, first of all, this sigma bonding MO is formed by combining a 1s orbital and a pz orbital. There is a node in pz orbital. So, this is what it will look like. Do not think it is an sp hybrid orbital or anything, it is not, it is molecular orbital. It is spread over the entire molecule. And for the antibonding orbital, what will it be? I will just draw the atomic orbitals in case there is any difficulty in understanding. In this case for the bonding interaction, this is your 1s orbital of hydrogen atom and this is the 4p orbital of chlorine atom. And you might remember that actually we are only showing the outermost lobe, inside you have shells, right, you have plus minus plus like that. But all we are talking about is the major shell. For further understanding please refer to that lecture where we had drawn these orbitals and we had explained how nodes are and how how wave functions are. So, this is the bonding combination of atomic orbitals. Anti-bonding combination would be if you put plus sign here, then it will be minus. So, you will have destructive interference here, that is how you get a molecular orbital that looks like this. You have constructive interference here, that is how you get a molecular orbital that looks like this. But please do not forget that your fluorine atom is here and sorry not fluorine, what is this, bromine, bromine atom is here and hydrogen atom is here, right. So, that is what we get from molecular orbital theory. In heteronuclear diatomics we get lopsided molecular orbitals and lopsided electron distribution consequently. Now we want to talk about carbonyl complexes. So, carbonyl CO, carbon monoxide is a very important molecule from the point of view of chemistry as well as physiology. It is known that carbon monoxide forms carbon monoxide uses this carbon atom as a good sigma donor in formation of coordinate bonds, and also it can accept pi electrons, they are empty d orbitals we say, right. Well, maybe d orbitals or what is it? No, sorry, I goofed up a little bit there. This d orbital is that of the metal. From there electron density can actually come back and be accommodated in some orbital of carbon monoxide, we will see which orbital. So, back bonding is there. This is called synergistic effect in inorganic chemistry. So, that is why carbonyl carbon monoxide can form very stable strong carbonyl complexes, and these complexes has applications in organometallic chemistry like the one that is shown here. You take a molecule like this, a complex like this, oxygen atom lone pair can attack say butyl lithium, okay, and then this R group, butyl group in butyl lithium, that gets attached to carbon. Once again carbon here is accepting electron pair and then whatever happens happens. So, the question is, why is it that carbon can act as a very good sigma donor and then how is it that it can act as a good pi acceptor also. Okay. To answer this question we construct a molecular orbital picture, but before that let me also state that carbon monoxide is important physiologically as well, because you might know carbon monoxide is a highly poisonous gas. It is highly poisonous gas because it goes and attaches with hemoglobin. Hemoglobin as we know is a carrier protein, it transports oxygen and CO2 in blood, and the way it does it is that this here is the structure, it is a tetramer and it is a metalloprotein. It has Fe2 plus and there is a ligand which is sort of like porphyrin heme, and then this is what happens. In the heme center initially you have a low spin complex. So, this Fe2 plus actually hovers above the ring and the 5th position is taken up by a distal histidine. Now, when from the other side oxygen or CO2 comes and coordinates, then it transforms to a low spin complex, size becomes smaller and this Fe2 plus goes and fits nicely in the cavity of porphyrin. Okay. So, that is how it takes up oxygen, that is how it takes up carbon dioxide, and it can give up oxygen and carbon dioxide easily wherever required. That is because these oxohemoglobin and carboxyhemoglobin, that is these complexes that are formed, they are formed reversibly. The problem is carbonyl, carbon monoxide forms carbonyl complexes that are extremely stable, the formation is almost irreversible. So, once that complex is formed, half life is of several hours. So, if somebody is exposed to carbon monoxide, all these or a lot of these hemoglobin molecules will form this very stable carbonyl complex with carbon monoxide, which is not going to break so easily. So, they will not be able to participate in oxygen and carbon dioxide transport that is most important for life processes, right. So, the question is, why does carbon monoxide form such a good complex? Why is it that it can be a good sigma donor from carbon, and why can the same carbon atom be a good pi acceptor? The somewhat contentious molecular orbital picture that has been constructed to explain this involves this concept of hybridization that we have discussed already. And here one thing I want to remind you is that it is not necessary that all hybrid orbitals have to be equivalent. They can actually have different energies. It depends on what alpha, beta, gamma, delta coefficients are. Now, with that background, this is the contentious model I was talking about. These are the 2s and 2p orbitals of carbon, once again more or less drawn to scale as far as energy is concerned. These are the 2s and 2p orbitals of oxygen. So, in the model that is used, remember we know the result already. To explain it, we are constructing a model, working out the energies and trying to see whether it makes sense. It might make sense to a certain extent and then it might not, we will see. So, so the model involves hybridization, formation of 2 hybrid orbitals, non-equivalent hybrid orbitals of 2 different energies for carbon as well as for oxygen. Okay. So, for carbon, H1 is a lower energy hybrid orbital, let us say, H2 is a higher energy hybrid orbital. Now, hybridization here we are talking about sigma bonds, right. So, hybrid orbitals accommodate sigma bonds, they are used for sigma bonding. So, the p orbital that participates in this hybridization would be Pz if we take Z to be the direction of approach of the 2 nuclei. So, Px and Py do not have the right symmetry as we have discussed earlier. So, they remain non-bonding orbitals on carbon, okay, right now. Well, should not even say non-bonding right now. They remain in a pure unhybridized form on carbon. Similarly, in oxygen you invoke hybridization, form H3 and H4, and Px and Py remain as such. So, now these Px and Py are actually available for pi bonding, we will come to that. Now, herein there is an objection. Why do we have to use H3 and H4 for oxygen? If you go back to homonuclear diatomics, we said that this mixing of sp orbital does not even take place for oxygen. So, why would it take place here? So, one argument is that the CO is isoelectronic with N2, right. If you compare nitrogen, oxygen has 1 electron more, carbon has 1 electron less. So, here even the oxygen atom should behave like carbon atom, that is the sort of the argument that is used, right. So, now let us try and see which orbitals have comparable energy and appropriate geometry. Do you think H3 will participate in formation of sigma bond? This is the energy of H3, this is energy increases, right, as you go up. H3 has very low energy compared to H1 and H2. So, it is going to remain non-bonding. Similarly, H2 has a little high energy compared to H4. So, it will remain non-bonding. The difference is H3 remains non-bonding on oxygen, H2 remains non-bonding on carbon. What about H1 and H4? Their energies are close enough. So, they form a linear combination to give you the bonding sigma orbital and anti-bonding sigma star orbital. What about Px and Py? Now, Px and Py are like this, these are x orbitals, these are y orbitals, they can form a pair of pi bonds, right. So, you can generate 2 sets of degenerate pi orbitals and pi star orbitals also, okay. So, when I write degenerate, it is important to understand what I am really saying is this. I do not think I talked about this earlier. So, I can write like this, I will call it pi x is equal to C1 Px of carbon plus C2 Px of oxygen. Pi y will be C3 Px of carbon plus C4 Px of oxygen, right. And similarly, when you take the antibonding combinations, you will have minus instead of plus here and the coefficients are going to change. So, here also symmetry becomes important. See Px and Px, let us say this is x axis now. They are in the right orientation, they have the right symmetry to participate in a pi kind of linear combination, but this Px and that Py do not. The two Py orbitals can participate in linear combination. So, while constructing these pi MOs, we do not take Pxc plus Pxo plus Pyc plus Pyo, we do not do that. We only take x's and y's. So, this is how the problem of formulation becomes a little simpler. Okay. Now, we have to fill in the electrons. How many electrons does carbon have? 2, 4, 2, 3, 4, right, 2 pairs. And what about oxygen? 2, 4, 6, 3 pairs. So, now we have 6 plus 4, 10 electrons, we will start filling them up in pairs. So, sigma Nb, the lowest one H3 is going to have a pair, sigma from H1 and H4 will have another pair, and we have 4 electrons more, they will reside in the pi orbitals, pi molecular orbitals, alright. Is there anything more? Yes, one pair in sigma Nb. Remember sigma Nb is a non-bonding orbital, that is an exclusive property, if you want to call it that, of carbon atom, right. It is localized on carbon atom. So, what we see is that this and sigma, right, sigma means it is going to be highly directional. Now, let me tell you the reason why this hybridization was done is that this is known to be used, well, this is what we think participates in sigma donation. So, if you want sigma donation to take place, you want a highly directional orbital. Hybrid orbitals are more directional than your p orbitals, right. So, that is why this hybridization was used in the first place. So, now this model nicely explains why CO can act as a good sigma donor through the carbon atom, because the highest occupied molecular orbital is a non-bonding orbital localized on carbon. And why is it that it can accept electrons? And remember the diagram I had shown you earlier. When we talk about synergistic effect, when we talk about back bonding, then this is the diagram I had shown and I had goofed up a little bit. This here is a d orbital of the metal ion. We drew an orbital on the same carbon of carbonyl like this. This has to be an empty vacant orbital, and we said this is how the electron cloud gets transferred. So, this d orbital is filled and the whatever this orbital is vacant. Okay. Now, remember this is the sigma bond. So, any orbital that is perpendicular to the sigma bonding orbital, what kind of orbital would it be? It has to be a pi orbital, and I will show you in a minute what these pi star orbitals look like, right. So, what we see here is that carbon also has these low lying vacant pi star orbitals which have the right symmetry, which enables it to accept any electron cloud that comes back from the central metal atom, d orbital. So, this is the orbital that is used in the action of carbon atom to behave like pi acceptor in carbonyl complexes. Now, let me show you the orbitals, molecular orbitals, and again this is a little contentious. What I would like you to focus on is this sigma Nb orbital. See, it is on carbon, heavily on carbon and pointed towards one side, it looks like a hybrid orbital, and this is the pi star orbital. Again it is close to the carbon orbitals, right, carbon px orbitals. Look at the bonding ones. The bonding ones are close to that of oxygen px py orbitals. The anti-bonding ones are actually lopsided towards carbon because they have a greater contribution from px and py orbitals of your carbon atom. Okay. This is a model that can nicely rationalize why carbon monoxide is such a good ligand, why it forms good sigma bonds to carbon atom, and why the same carbon atom can efficiently accommodate electron cloud coming back from the central method atom. That brings us to an end of our discussion of heteronuclear diatomic molecules. In the next class we are going to go back to polyatomic molecules, but this time we are going to learn how one can use molecular orbital theory to understand polyatomic molecules.